Welcome to a new video about analog electronics. We continue with our design examples, and in this video we will discuss the design of an integrator circuit. There's a circuit given and we need to determine the component values for some specifications in this circuit. Of course, we will work out the calculations step by step and also verify these in SPICE simulations and also check that in the measurements and compare all of them. So let's look at our assignment. The objective for this assignment is that we need to design the circuit shown next. That's actually shown here. So we see here an integrator circuit actually. And we need to determine these three component values. Now we have the following specification. Input resistance must be 20 kilo ohms. The unity gain frequency must be 50 kilohertz. And we have the cutoff frequency of 12 kilohertz. So three specifications. So if you have three specifications and three unknowns, so we have then a unique set of solutions. The requirements is that we need to draw the design circuit completely. We have already the circuit, but we need to give the component values and also to compare the calculation, simulation and the measurements. We will do that also in the next steps. And we also need to prove that the specifications are met, or we need to discuss if we need to tune or not in our design steps. And we need to use the exact component values and also the correct models in the simulations. Okay, let's start directly with the mathematical expression, which is our transfer function for this circuit, because we go from VI input to the VO output. So we can have the transfer function here in the Laplace domain, which is given by HI, which is for integration, and S for the Laplace parameter, which is then minus ZA over ZB. Why minus? Because this is an inverting integrator. And the ZA here is the parallel combination of the R2 and the capacitor C. That's shown here, the first one, so the R2 and the reactance of the capacitor C. And the parallel combination can be also written like this. And if you look at the formula for the reactance of the capacitor, which is 1 over SC, you have now this expression, and if you now simplify this, you get now this expression for ZA. ZB is actually purely resistive, so that's just R1. And then we can now substitute these two expressions in here. Then we have the following expression for our integrator. Now we can simplify this by multiplying the numerator and denominator by 1 plus R2CS. Then you have this nice expression. Okay, now what we have is now that we see some gain at DC and some cutoff frequency also in our expression. Okay. We can also write it like this, in this form, that we see it again, and we can also convert that in the J omega domain. Then you have this, and this is useful later for the future calculations for the frequency analysis. Okay, now we have our transfer function, so we can move on. Then we need to now look at these three specifications. The condition 1 or the specification 1 talks about the input resistance or input impedance. That is looking at this node into the circuit, and then you see actually the Rin is R1. Now since that must be a 20 kilo ohms, that is already given, so we have only now two unknowns because R1 is already determined. The condition 2 is about the unity gain frequency. That must be 50 kilohertz. What does the unity gain frequency means? That is actually the frequency where you have a gain of 1 or 0 dB. So at 50 kilohertz, we need to have a gain of 1. That means the following: the absolute value of our transfer function at that specific frequency, which is called omega sub t, the absolute value must be 1. Okay. Now we know that this transfer function absolute value can be given by this expression. And then when you substitute in here for omega sub t, that must result in 1. Okay, now we can rewrite this. We can now say R2 over R1 divided by 1, that's actually shown here, is equal to this square root for term. And we can now rewrite it also in R2 is equal to R1 times the square root. We have now this expression. Okay, let's call this equation number 1. We will use this later. The condition 3 about the cutoff frequency means the following actually, that our transfer function, again in the absolute form, at that specific frequency, which is omega c, which is 2 pi times this frequency, must be equal to 1 over the square root of 2 times the low frequency gain. This is the definition of the bandwidth or the cutoff frequency. What is the low frequency gain? Now let's first look at the expression here, because this is the expression what you have for the absolute value of the cutoff frequency from here. So R2 or R1 again, and then the square root of the 1 plus the omega c R2 times c. So it's actually product, again quantity squared, must be equal to 1 over the square root of 2 times R2 over R1. And this is the low frequency gain. I will show you that shortly. This is the low frequency gain. Why? You can see that in the circuit here, if the capacitor is, let's say, operating at 0 frequency, let's say 0 Hertz, then this is an open. And then the only gain what you have is just an inverting amplifier, which is an R2 over R1, of course with a minus sign, but in absolute sense it's just R2 over R1. Now that's shown here. Now you have already here the left side R2 over R1 and also the right side, so you can cancel them out. That will result in this one. Now since this must be equal to that one, that means actually this in the denominator, which is an omega c R2c product quantity squared, must be also 1. That just mathematically seen here, and then that will result in this formula for the cutoff frequency, which is then 1 over R2 times C. Okay, now let's call this equation number 2. Now if we now substitute this equation number 2 into equation number 1, so actually what you have is then the following. You use R2 times C as 1 over omega C. That's actually what I mean. Then you get actually the following, because then you have already omega t divided them by omega c or multiplied by 1 over omega c. That's actually shown here, and the quantity must be squared. Now this is actually a really nice formula. You see actually the specifications we have given: unity gain frequency, the cutoff frequency, of course in this case omegas, but it doesn't matter, and we have R1 and R2 in that relationship. You can also say, now let's, instead of using omegas, the frequency is in hertz. That's also possible because that's a ratio. That's also fine. So we can just use this formula. Now let's call this equation number 3. This equation, we can calculate the required ratio of R1 and R2, and then consequently their individual values given the specifications for the unity gain frequency and the cutoff frequency. Now let's move on and then do that. Now from the condition 1, we already said that we have an R1 is equal to 20 kilohertz, so we can, kilo ohm I mean, we can just substitute in here. What do we have now? So actually we have already R2, if you look at it, because R2 will be then 2 times 10 to the power 4 times the square root of 1 plus and then 50 kilo ohms divided by 12 kilo ohms squared. That will result in 85.7 kilo ohms. Okay, so we have also R2. So we have R1, we have R2. The only unknown is the capacitor C. Now finally we can calculate the capacitor C from equation number 2. Just rewrite this capacitor formula. So C is then equal to 1 over the R2 times omega C, or omega C times R2, doesn't matter. You have now this, of course, always 2 pi times the frequency in hertz, and the calculated R2 here, that will give us 154.76 picofarad, or almost 155 picofarads. So we have now all 3 components. Okay, and this is now the transfer function. If you substitute the values for R2, R1 and C, you can see that here, and when you simplify this, you get now this expression. Again, remember we have a minus sign because there is an inverting action in this circuit. Now let's collect them together and look at the simulation result. We start with the first ideal op-amp case, just to look that this circuit is working in ideal situation, because if this is not working in ideal situation, it is hopeless in a practical situation. Now what you see here, we use a set an ideal op-amp. Now this is the transfer function. Let's go to the low frequency gain. This is this. Now the low frequency gain must be 4.285 in the scalar form. If you do now 20 log of that value, you will get really close to this value. So this is fine. You'll see that at low frequency that you have a phase shift of 180 degrees or minus 100 degrees. So that is also proven. You see that the cutoff frequency, or the, let's say at 12 kilohertz, you see that the gain has now decreased by 3.01 dB as required. So this is also verified. You see also the phase there, because it must be then decreased by 45 degrees. So you see that actually also here. Now, the next one is our unity gain frequency. So you have 0 dB at 50 kilohertz. So all the specifications actually are met. So we can say this is perfectly fine. Again, it is an ideal op-amp. So it is good that we check this, but it is not what we should use. So we move on and then use the model of, in this case, the TL072 op-amp in the simulator. What do we get now? Okay, this is now the situation for that circuit with that model. Now the low frequency gain is still fine, so that is no problem. Also the phase is fine, but there are some problems in the cutoff frequency. You see the cutoff frequency is now 11.82 kilohertz, so it's a little bit lower than 12 kilohertz. You see also that the 0 dB is not achieved at 50 kilohertz, but it's 49.27 kilohertz. The error is not that much, but there is an error, so we need to also tackle this later. Okay. Now, what is possible in order to get that 50 kilohertz for the unity gain frequency and also the cutoff frequency of 12 kilohertz? You can say, let's adjust something. Now, that is, in this case, the capacitor that is predominantly affecting these two values. So that is now adjusted. In this case, we have this plot, and then the capacitor value is now changed from this, the initial value of 154.76 picofarad to 152.5 picofarad. So it's lowered in order to get the right unity gain frequency and the cutoff frequency. Just try an error. So there is no exact science in this one. Again, the low frequency gain is fine, but you see this circuit will be then used. You see the TL072 for the op-amp model in the T90i simulator. R1 20 kilohertz, kilo ohm I mean. The R2 85.7 kilo ohm, and you see here the new capacitor value of 152.5 picofarad. Now let's go to the specifications. Low frequency gain is as before, so that's fine, and also the cutoff frequency is also achieved at that 12 kilohertz, and also the unity gain frequency of 50 kilohertz. So you see 3 specifications are met, and also the input impedance is also achieved. So you can say this is perfectly fine by just adjusting the capacitor value. Okay. Now let's then move on and see what we can do in this case. Now the measurement results are of course very important. Now we measure the circuit using this op-amp TL072. But in order to get the R1 and R2 very close to what I have originally calculated, I could not get any closer than this one, so I have now 19.92 kilo ohms. So that is fine. So slightly lower than what I have here, and this is what I have is 86 kilo ohms, so it's slightly larger than what I have here. The capacitor I have here is almost the same, but slightly larger, so you can see that the 0.2 picofarad larger. What do I have now? Now let's look at the first low frequency gain. Now my input in this case is 6 volts peak, so symmetric sine wave. And my output, you can see that here, the blue, so the yellow is the input and the blue one is the output. It's inverted, so that's already a verification. You can also see that the phase here, almost 180 degrees. It is now 26 volts peak. Now that will give me in the scalar form, so output divided by the input, 4.33, which is 12.73 dB. So close to what we had in our simulations of 12.64 dB, so this is perfectly fine. Now, moving on to the next step, which is the cutoff frequency. Now, there you get some issues. This is for the case where we have these values again. You see the following. Now, the peak value for our input, the yellow one, is still 6 volts, but the blue one here gets at 12 kilohertz a value of 19 volts peak. Now when you now do this 19 over 6, you will get a gain of 3.17, which is 10 dB approximately. But in order to have the cutoff frequency, we need to go now to 9.72 dB, because that is 3.01 dB lower than this low frequency gain. So there is an error here. Now, where do we get this actual value of 9.72 dB? Now, looking at the plot on the right side, the gain indeed decreases by 3.01 dB, but not at 12 kHz, but 12.8 kHz. That's actually shown here. So at 12 kHz, I don't get that. At 12.8 kHz, I get the cutoff frequency, but it is 800 Hertz off. So we have an error of 800 Hertz here. Now, we need to tune this. Again, we will see that shortly. Let's also look at the unity gain frequency, how much error we have here. So for the cutoff frequency, we have an error of 800 Hertz. Now, the left side is the plot for the unity gain frequency calculation. You see the yellow is again the peak value for our input, and the blue one is the output. But the blue one is 6.2 volts at this 50 kilohertz. But it must be exactly 6, of course. So in order to have a gain of 1, the error is not much, you can say, but it is some error. And since this is not exactly what we wanted, we need to look at where we get that gain of 1 or 0 dB. Now, when you increase now the frequency to 51.9 kilohertz, then you get what you actually want, which is then 6 volts over 6 volts, which is then the gain of 1 or 0 dB. Now, in this case, we need to increase from 50 kilohertz all the way to 51.9 kilohertz. So the error here in this case is 1.9 kilohertz, so it's larger. Okay, you might say, okay, this is fine. I don't really mind about the error of cutoff frequency and a unity gain frequency, so I just built this. Probably also fine for most cases, but let's see what we can do. I've actually tried to tune this and looked at the capacitor value. Now, I also increase the capacitor value from what I had before to 166.6 picofarad. So in this case, everything is the same. So the R1 and R2 are exact same as before. I only changed the capacitor. So increase the capacitor. Now, the left side is the cutoff frequency plot, or the measurement in order to determine the cutoff frequency, and for the right side you see the unity gain frequency. Let's start here. What we see here now, the gain here, again the input is, by the way, 6 volts peak, or the yellow one, and the blue one I see here 18.38 volts. You can also see that also here, the peak value. I measure that, by the way, using cursors to get it more exact. Now, when you do the calculation here, you get now here 9.72 dB. When you look at the scalar value, that happens at 11.9 kilohertz, which is what we wanted this value. But of course, at 12 kilohertz, I have still an error, but that error is now decreased from the previous case from 800 to 100. So I think a quite achievement. But looking at the unity gain frequency plot, because I have the yellow one, which is again 6 volts peak, and the blue one must be also 6 volt peak. Now, at that frequency, that happens at 48.6 kilohertz. You see that again, the blue one is 6 volts peak. Now, the gain is indeed 1, but not at 50, but at 48.6 kilohertz. So, again, there is some error. We, by the way, again, improved the, let's say, the error, or reduced error, because error was before 1.9 kilohertz. Now we have only 1.4 kilohertz. Still maybe not good enough, so we can say this is still too much. Then we need to tune this further. In this case, I just said this is for my case, let's say the endpoint for my design cycle, and I accept this error of 100 hertz in my cutoff frequency, and also accept this 1.4 kilohertz in my unity gain frequency. And now the design is actually completed. But let's also summarize the results. This is the circuit we have given. These are the specifications. This is the R1 and R2 I have used. And in case 1, we had the following with this capacitor value. The cutoff frequency was 800 hertz off, and the unity gain frequency was 1.9 kilohertz, or 1900 hertz off. But for the right side, which I have chosen for this case as the final choice, is the cutoff frequency is pretty close, and the unity gain frequency has improved, but still some error in it. Alright, this is our example about the integrated circuit design from the specifications about the input resistance, unity gain frequency and the cutoff frequency. We have seen how we can determine that from the transfer function, the values here in the circuit, and also if there are some tuning needed for this circuit, and we have seen that this is indeed required. Remember that you always need to start with the simplistic model, in this case ideal models, ideal op-amp circuits, and then move on and then build the model more complex in order to check what is happening. If you have any questions, comments about this complete design example, please let me know. I will try to answer them as soon as possible. See you next time in another video.